Hello. In the previous clip we looked at feedback control problem as one which allows us to get the output of a plant x of t to track a reference r of t in the presence of uncertainties either in the plant model or in its environment in the form of disturbances. And I have sketched here the basic block diagram for the feedback problem. We have a sensor that measures the output of the plant that we want to control, which I have called P here, and then compares it with the reference, and the difference is manipulated by a high gain function H, and the output of the high gain function is fed back to the plant. Now what is quite interesting is to note that practically every single control engineer is ultimately implementing this block diagram in one form or another. So it is the high gain of the controller that ensures that x of t would be equal to r of t. So what are the typical controllers that we might have come across? The most common controller is the on off control, which we see in our refrigerators, in our air conditioners and many other such thermal systems. So what do we have there? We have the output u of the controller to be related to the input E in terms of a step change. So if E is greater than 0, u is plus 1, if E is less than 0, u is minus 1. One can view this kind of a control action as the limiting case of a linear controller with saturation. This is the error and this is the output u, and in the limit that the slope here k tends to infinity, we would have on off control. So one can therefore view on off control as another version of the high gain controller where the gain k is tended to infinity and there is saturation that limits the output of the controller. So this is therefore a simple example which one might not have realized as a version of high gain control, but is actually the case. So in the case of on off control, we would have the control law to be of the form u is equal to sine of E, where sine is a signum function where given by sine of x is equal to plus 1 when x is greater than 0, 0 when x is equal to 0 and minus 1 when x is less than 0. But this is not necessarily the only way in which we can implement high gain control. There are several other control laws that have been developed over the last half a century or so. One other simple extension to what we just discussed now, namely on off control, is what is known as sliding mode control. In sliding mode control, we would have u to be the sign of not the error E, but rather some dynamic function of error, for example E dot plus E. Now what happens in this case is that when this kind of a control law is applied, then the system moves to the surface E dot plus E equal to 0. So this is a surface in the phase space of error and its derivative. Now this particular term that we have inside the signum function is a choice of the control designer, and we choose such a dynamic function of the error that it is stable and the roots of this characteristic polynomial are sufficiently fast for the error to decay down quickly. So this kind of control strategy, which is a general version of on off control, is called sliding mode control. So we see that even in case of sliding mode control, we have this high gain relating the input to the output that is responsible for getting the reference to be tracked by the closed loop system. Now all these, the two techniques that I talked about here are nonlinear control techniques. There are several others, some of them linear, some of them nonlinear, but it is satisfying to underscore the fact that as far as getting x of t equal to r of t is concerned, all of them attempt to achieve high gain for the controller. That is also true in case of linear control, with the exception that the input output relationship for a linear control system would be a linear system itself. So if I have a controller C here So, if I have a controller C, then if C represents a linear system, I can obtain its transfer function C of S, and the relationship between E and U is therefore going to be given by U is equal to C of S times E of S. And if my plant is also linear, then we would be dealing with linear control systems. Now, one would naturally want to wonder if this notion of high gain is also valid in case of linear control systems. Indeed it is so, but it is not easy to visualize it if one were to stick to the Laplace domain. However, it is obvious when one goes to the Fourier domain. So, if one were to look at C of j omega, so one were to obtain the transfer function and represent it in the Fourier domain and represent the plant also in the Fourier domain as P of j omega, then we would have x of j omega to be equal to P of j omega times U of j omega, and x of t to be equal to integral minus infinity to infinity 1 by 2 pi x of j omega e to the power j omega t d omega, and if I were to represent it in terms of u, I would have this to be 1 by 2 pi integral minus infinity to infinity P of j omega u of j omega e to the power j omega t d omega. Now, I can represent this term P of j omega times u of j omega in terms of the reference R and the plant transfer function P as C times P by 1 plus C times P of j omega times R of j omega. This would be equal to P of j omega times U of j omega. If I were to replace that in this equation, I would get x of t to be equal to 1 by 2 pi integral minus infinity to infinity C of j omega P of j omega by 1 plus Cp C of j omega times P of j omega times R of j omega e to the power j omega t d omega. So, what we see therefore is that in the frequency range where C of j omega times P of j omega is much greater than 1, then the term here would be very nearly equal to 1, because C of j omega C times P divided by 1 plus C times P will be approximately equal to 1, and so if the frequency content of the reference is such that it is matching with the range within which C times P is much greater than 1, we would have x of t to be approximately equal to 1 by 2 pi integral minus infinity to infinity 1 times R of j omega e to the power j omega t d omega, and that is equal to R of t. So, indeed therefore that a high gain for the controller is necessary even in case of linear system analysis to get x of t to be equal to R of t. However, there is one central concern for all the different control strategies that have been developed in the past. So, while the trick for getting x of t to be equal to R of t is very simple and is common across all control techniques and for all plants that one might wish to consider, the really important bottleneck that every one of these controllers have to address is the issue of the stability of the closed loop system. It can be easily shown that when your controller gain is very high, your closed loop system can potentially become unstable, which means that some of the poles of the closed loop transfer function would go on to the right half of the complex plane. It is therefore imperative for us as control engineers to simultaneously wear two hats. One is the hat that we would wear when we are trying to do performance engineering, in other words getting the output of our plant x of t to track the reference R of t with the desired accuracy. The second hat that we would wear is one of stability engineering, wherein we try to make sure that in our attempt to get x of t to be equal to r of t with the desired accuracy, our closed loop system has not become unstable, in which case our entire effort at getting the controller to have a high gain would be futile. It is therefore very important for us to have tools at our disposal which will tell us if our closed loop systems are stable or unstable. So let us remind ourselves what transfer function we are talking of here when we are interested in the stability. The transfer function that we are looking at is the one that relates the output x to the reference r, and that is going to be given by c times c of j omega times p of j omega divided by 1 plus c of j omega times p of j omega. It is stability of this system that we are interested in, and to assess the stability of this system it is useful to represent the transfer function in the Laplace domain rather than in the frequency domain. So the frequency domain representation that we looked at in the previous slide was very useful to convince ourselves that x of t would be equal to r of t when c times p is very large. So c times p therefore had a very nice physical meaning of a gain which needed to be large in order for our control performance objectives to be met. But as far as stability objectives are concerned, it is useful to come back to the Laplace domain, in which case we would have the transfer function g of s to be equal to c of s times p of s divided by 1 plus c of s times p of s. Now one has to determine the stability of this transfer function. So in order to do that, we know that for the systems that we would be working with, we would have our controller and plant to both be represented by linear time invariant ordinary differential equations. Therefore both c of s and p of s would be the ratio of two polynomials. So when I take their product, they too would be the ratio of two polynomials, let us say n of s and d of s, in which case g of s would be equal to n of s by d of s plus n of s. Now we look at the roots of the denominator polynomial, and we need to make sure that the roots of the denominator polynomial, which are the poles of g of s, are stable, or in other words they are on the left half of the complex plane. If they are on the left half of the complex plane, the impulse response associated with this particular transfer function would all comprise decaying exponentials, and therefore our closed loop system would be stable. Now the question is, how do we go about determining whether the roots of d of s plus n of s are stable or unstable? Well, if the degree of the denominator polynomial is 1, it is obvious. So if let us say n of s was some constant k and d of s was some term of the kind tau s plus 1, then we can by inspection tell that d of s plus n of s would be equal to tau s plus 1 plus k, and we can clearly tell the conditions under which this system would be stable, namely that 1 plus k by tau should be greater than 0. So it is possible even by just visual inspection to determine whether a first order closed loop system would be stable or unstable. For a second order closed loop system, it is not that straightforward. One has to solve a quadratic equation, because in that case d of s would be of the form s square plus as plus b, and n of s could be either a constant or could be some linear function of s, or at most a quadratic function of s, and therefore one d of s plus n of s would be a quadratic polynomial, and one can still determine its roots by analytically solving this quadratic equation. If our d of s is a third degree polynomial, then it is still possible to obtain the roots of a third degree polynomial. There are several techniques available to factorize third degree polynomials, and therefore be able to tell where the roots are and whether those roots are on the left half of the complex plane or the right half of the complex plane. If you come to the next level of complexity, namely fourth degree polynomials, then it is possible to factorize a fourth degree polynomial into two quadratic polynomials, in other words second degree polynomials, and then subsequently obtain the roots of these two second degree polynomials. We are not sure whether our closed loop system would be either a fourth degree or a third degree polynomial, depending on the complexity of the system. It could be a fairly high order system, in which case let us say we have a fifth degree polynomial for d of s. Now there are theorems in mathematics that say that it is not possible to factorize a general fifth degree polynomial, and the same is applicable for higher degree polynomials as well. Therefore, our initial attempt to determine the stability of the closed loop system by identifying the locations of the closed loop poles directly by factorizing the denominator polynomial is not going to take us very far. It can take us at most to addressing the stability concerns up to a biquadratic or quartic polynomials, fourth degree polynomials, but not beyond that, and there is no guarantee that our plant times the controller would have a denominator polynomial that would be of the fourth degree and not more than that. Also, we note that as engineers we are not just interested in determining the stability or answering this yes or no question of whether it is stable or unstable, but we want to be able to improve its stability. We want to be able to engineer the performance such that it has a desired amount of stability and a desired speed of response. This approach of determining the zeros of the denominator polynomial does not lend itself very well to our engineering intention of being able to tune the parameters of the closed loop system to achieve a desired performance. So therefore, what other approach do we have at our disposal? One other approach is what is known as the Routh array, which you must have come across in your undergraduate education. The Routh array looks at the denominator polynomial and uses a Routh table in order to determine whether that polynomial is stable, has stable roots or not. As powerful as it is, Routh array has this issue that it assumes that the coefficients of these denominator polynomial are constants. However, as I discussed, control system designers often have to deal with plants whose parameters might be uncertain and which might change with time and so on. Therefore, while Routh array is definitely useful in the context when we have fairly good knowledge of the plant's parameters, it does not work as well when we have uncertainties associated with the plant's parameters. Hence, what we would look at now is an alternate technique of determining the stability of the closed loop system, and that is based on the Nyquist stability theory. So the subject of today's clip would be Nyquist stability theory. Now if we come back to this problem of determining the stability of the closed loop system, we note that it is not really necessary for us to tell exactly where the closed loop poles are. In other words, it is not really necessary for us to tell the exact roots of the denominator polynomial of the closed loop system. All that is necessary or expected of us is to check whether any of these poles are on the right half of the complex plane or not. If this one decision can be made without even knowing exactly where these poles are, then we are good. We would know whether our closed loop system would be stable or not. So Nyquist stability theory answers precisely this question, but it does more than just that. It allows you to tell whether you have closed loop poles in any part of the complex plane or not. So if I have a general complex plane, what Nyquist stability theory allows me to determine is whether you have any poles of a particular closed loop transfer function in any given region within the complex plane. So if I were to demarcate a closed region within the complex plane by its boundary C, then I can apply Nyquist stability theory to tell me whether a function f of s has poles or zeros within that region, and the power of this technique is that I can do it without actually having to factorize f of s and determining exactly the locations of its poles and zeros. So, in order to illustrate how Nyquist stability theory works, let us take a numerical example. Let us start with a very simple function f of s is equal to s minus a. Now, what is expected to start with is to verify whether the 0 of this polynomial f of s equal to s minus a is within this closed contour C or not. Well, you might say this is a very simple trivial problem, because I know that the 0 of this polynomial is s is equal to a. I just locate this point s is equal to a in the complex plane wherever it could be. It could either be here or it could be there. It might depend on the exact numerical value of a, and I just see whether this point is inside this contour C or outside that contour. So, visually I can tell. Well, that is so, but suppose we were to impose this further restriction that you are not allowed to locate a within the complex plane, but yet you are asked to tell whether a is within C or not. How would we do it? So, this is where we would have to employ Nyquist, the concepts of Nyquist stability theory. The reason that we want to do this is because in real life our f of s, which would be the denominator polynomial of our closed loop system, cannot be factorized. So, we cannot tell exactly where its roots are, but yet by doing a few simple tests based on Nyquist stability theory, we want to be able to tell how many of the zeros of f of s are within the contour C. And in the case when this contour C encompasses the entire of the right half of the complex plane, then we would have we would be in a position to tell how many of the zeros of f of s are on the right half of the complex plane. So, let us start off with this function f of s. For the moment, let us assume that the point A is inside the contour. Now, let me consider a general complex number s on the contour. So, the complex number s is represented by this particular phasor. This particular phasor here is the complex number A. Therefore, this complex number is essentially s minus a. Now, if I were to take this complex number which is on the contour C and take it round the contour in the counterclockwise direction once, what will happen to this complex number s minus a? If I were to graph this complex number s minus a, so in other words the real part of s minus a versus the imaginary part of s minus a, in the present configuration the complex number looks something like this. Now, when I take the variable s around the contour C, what would happen is that the end of this complex number would trace a curve that is similar in shape for this particular case to the curve C, and what is more significant is that it goes round once and therefore encircles the origin once. The angle of this complex number s minus a changes by 2 pi if the point A is inside that contour. On the other hand, let us take the other scenario where the point A is outside this contour, in which case once again if we were to consider a point S on the contour, we would have s minus a to be this complex number, and when we take the point S in the counterclockwise sense around the contour once, then what would happen to this complex number s minus a? If I were to keep track of the change in angle of this complex number, what I would notice is that the net change in angle of this complex number s minus a would be 0. So, in other words, it would execute a motion that would trace again a curve similar to C in the plane that plots real part of S minus A versus the imaginary part of S minus A, but in this case it will not encircle the origin. In other words, the net change in phase of the complex number S minus A will be equal to 0 in this case. Therefore, I have this one nice test wherein even if I cannot locate the point A in the graph paper where I have drawn my curve C on the complex plane, I can still determine whether A is inside that curve or outside that curve by looking at whether that curve encircles the origin in the f of S plane or does not encircle the origin in the f of S plane.